Welcome back to the channel. Hope everybody's doing well. And in today's video we are taking a look at the Uni-T UT505B Insulation Multimeter that has arrived in time for Christmas. Purchased this from Amazon, took about 3 weeks to get to me. I did get this for quite a good price, but at the current time of doing this video the price is £253 on Amazon. Searching along other suppliers, I'm picking up prices from £205 all the way up to £760 on some eBay sellers, so quite a price range for this instrument. For what you get for your money, it comes in a cardboard box, as do a lot of the Uni-T instruments, and then inside the box the meter itself comes in a little canvas bag / case. There is a carry handle for this, but that's it. There's no Uni-T branding on this or anything, and the actual packing within this is quite minimal. There's a little bit of padding in the front here and in the back around the sides. It's just the thin sheet of material there, so not much to speak of. The actual meter itself we can get out and it's put in there for you, and then we get a remote probe for use with both insulation testing and continuity testing. We get the leads themselves, which are silicon, and we get a couple of crop clips, these two here, and then a couple of probes that I haven't even unwrapped yet. So there's the probes there, black and red as per normal, and then finally you do get an instruction manual with the instrument. This is completely in English. It's not the best of English. It does take a little bit of reading to get to fully understand it, but it's fairly comprehensive. It takes you through all the functions in there. We've got the specs at the back there, and then we've got one for each operation, such as that there, the capacitance there and resistance there, and you get a little diagram to show its use and a step-by-step instruction for the function that you're measuring. So that's what you get in the actual kit. We'll take a look at the leads themselves to start off with. Okay, so the leads themselves, they are silicon insulated leads. If you look at the actual designation, they are 18 gauge, 150 degrees C, 6000 volt leads. So pretty well insulated in that respect. At the end the jacks are inline jacks. There's no right angle jacks on this, either for the instrument or the accessory end. You can see them both there. Strain relief on these is not the best. You can see an actual gap in between the lead insulation and the collar of the strain relief there, so I'm not sure how well that will fare over time, but they're nice and soft and subtle, and seem to be of reasonable quality. We're set up for 1000 volt test, so we'll put that on, and you can see we've immediately gone to greater than 200 gigaohms. If I take hold of the leads, you can see it drops down, but then it does start to pick back up again. If I grab hold of the leads a bit tighter, we'll see what happens. So again, the same response as before, in that the insulation initially dips and then goes back up to 200 gigaohms. So seems to be pretty good quality for these leads with regards to that aspect. We'll just turn him off so I don't zap myself. So we take a look at the probes. You can see these are GS38 probes, so they're 4mm plug and play, so easily compatible with other leads and accessories. The probe tips do come off to reveal a 4mm probe tip there that you can put an accessory onto. And if we look at our actual terminal rail here, you see we're set to ohms, so if we there's our 0 kilo ohms there. And if we swap them over, go with the cap, you can see, let's do it the other way. You can see our 2.5 has got no chance of getting in 4s. 6 mils, we can't quite actually make contact. Oh, we do actually make contact, but that's jammed in quite badly, so not the best approach. But if we go without the probe cover on there, then, or the tip cover I should say, you can see we can get into, there's our 2.5s in there and our 4s, so you can easily access the terminals with the probe cover removed. Let's go over to our other terminal rail and we can move to crop clip. Crop clips have got reasonable capacity on them. So they will go over the probe like that, but they will also fit directly onto the lead itself, which is my preferred method. Got our M12 stud there. That goes around the thread, no problems. Will just about go onto the nut itself, and then we can get into 10mm, no problems with the cap on. But again, these are our 4s again and 2.5s, the Weidemuller versions. That's a 6 down there, which again we can't get into, so we have to remove the cap, and then we're away again, getting into them. So yeah, not the best of probes, but obviously easily replaceable with it being a standard 4mm accessory. So that's that all covered off. As alongside the standard probes, we do get a remote control probe. So let's move over to our continuity. This is the remote probe. Again, same kind of functionality. You can take off the cap there to reveal the standard 4mm probe tip underneath. Let's plug him into the instrument, and we'll just go to continuity test. Now the continuity test is an auto, you have to manually trigger this. Let's put our crop clip on there so we can get in with the 10mm, no problems, and we test it. And because the reading is over 100 ohms, I'm getting an open circuit reading, but if we go on to the actual stud itself, you can see we do get a reading there. So the test times to lock on because I've got the lock facility up there. Let's turn it off and let's remove the lock, and then you can then control it on the button itself, and it starts and stops straight away. You can't get into the actual 4mm and definitely 2.5s again. If you take the cover off, we're straight in, no problems. So that's the remote control probe, works perfectly okay if you like to use that kind of thing. So that's that done, and we'll move on to the instrument functionality. So we are set up for AC voltage measurement using the DMM Check Plus. This should be kicking out 5 volts AC. You can see we are reading 4.97 volts, and we have the frequency, which should be 50 Hz at 49.9 on the secondary part of the display. Voltage wise, we are 0 to 600 volts, and we are Cat4 measurement at 600 volts. Resolution is 10 millivolts, and accuracy is plus or minus 1.5% plus 5 digits, so we are well within the accuracy there. Shifting around to DC volts, and we are flipping him back up to there. We are 5 volts DC, measurement smack on. Again, DC voltage is 0 to 600 volts with a 10 millivolt resolution, and accuracy on this range is plus or minus 2% plus 3 digits. What I didn't mention about the frequency is that is 45 to 1 kilohertz range with a 0.1% plus 3 digits accuracy. So we'll just shift over to our continuity function. We've had to change the position of the jacks on the instrument. This is driven by the test switch or the remote control probe. We have a 20 milliamp setting, which is 0.01 ohms to 100 ohms, plus or minus 1.5% plus 5 digits. Or we have a 200 milliamp setting, which is 0.01 ohms to 10 ohms, plus or minus 1.5% plus 4 digits. We are currently on a 2.2 ohm resistor reading 2.27 ohms, so yeah, that looks to be in tolerance as far as I can tell. So with our continuity functionality, we also do have a 0 as well, so we've shorted the leads out and we press in, hold in on the comp, and it does 0 itself there. So if we then change the reading out, we were 2.27 earlier, now we're 2.21 ohms with the 0 set on it, so we're getting a much more accurate reading there with that aspect of the functionality. Let's swap over onto the higher resistance values and plug into our resistance box. We are currently reading 0 ohms, 5 ohms there. Let's go back to 0, let's go to 1k, 0.99k, so fairly accurate. 100k, we've got a smack on 100k, 99k, and then we'll go up to 10 mega ohms is the maximum it can read, and our tolerance on resistance is plus minus 3% plus 3 digits, and there you see 9.9 mega ohms, perhaps a little bit slow to range, but it does get there and seems to be good and accurate. So that's that one out of the way. We do have capacitance function on the same position of the selector switch. To get to that, we hit the select button over there, and we've changed to capacitance now. For capacitance, we are 0.1 nanofarads to 500 microfarads. 5, so at 5 we're starting to register now with 0.3 nanofarads, so it's a little bit out at the lower end of the capacitance. Let's go to 1 nanofarad. And we are 0.8. We have 10 microfarads on there. Let's go the other way and go 90 microfarads. And see, it's quite slow, fairly reasonable to respond. 93.9 microfarads there. So possibly a little bit out, but it looks to be within tolerance. Let's pull that out there. And we'll just bring in our 300 microfarad is the largest I can go to for a test capacitance. So we'll plug that in and see what happens. 318.5, fairly quick. 319. Yeah, I'll have to do some calcs on that to see if that one's in spec, but it's fairly fast to respond, but it is a little bit out from the 300 microfarads. So that's the capacitance function done there, and that's the end of the multimeter functions. We then move more onto our insulation test functionality, so we'll have to get the winding simulator out for that. So just before we get into the insulation test function, generally when you do a motor you will also use the low ohms function to measure the winding resistance. I have here a couple of my simulators, and I've been struggling to get this UT505B to operate. We have here the MTR105. I've set that up for 2-wire resistance mode, and I'm using the leads from the UT505B. We'll just put them together, and we've got 0.09 ohms. So if I zero that, got a 0 there, and if I go on to my winding simulator here, the full motor one, we get 3.49 ohms. This should be 3.5 ohms nominal in star mode. 3.57, 3.58 and 3.53, so we're all good there. We'll just do the same with our UT505B, so we're in the continuity. Short the leads out, hit the test button, 0.07, so we'll zero that. There's our 0. Go on to our simulator. So we'll set up onto the simulator, hit the go button, and we've got 9.09 ohms, so that's 2.5 times what it should be. Go on to one of the other ones. Sometimes it doesn't seem to like this. If you reset, then it goes starts to behave well, gives you a lower reading that we'd normally expect, but still quite a bit more than what it should be. Again, it's done the same again. It's dropped to 20 milliamp function, and we're 99.3 ohms. Stop it, restart it, and we get 9.08 at 200 milliamps. So yeah, not 100% sure. This one at the back here, this should be 36 milliohms, so we'd be looking at 0.04 on this. Now we do go straight to 200 milliamps, but we've got 0 ohms, so I'm not 100% sure. It doesn't like that at all. We'll take the 0 off, and then go back into test, and you've still got 0. So doesn't like it, does it? Let's just go back to the MTR 105. We're on to with 0.05, so we're a little bit out, but obviously 2Y measurement of 36 milliohms is always going to be problematic, but we're much closer with that than we are with the UT505B. So I'll just flip this over to Delta mode so you can see what it does in that mode as well. So just go back to Delta mode on our simulator there, and we've got our MTR 105. We are 1.20 ohms, so that's all okay. Let's flip over to our UT505B, and we'll just show you what that does. We'll hit the test mode, and you get a brief 6.93, which is still way over the 1.2 ohms. But we move to this FU, which I presume is fuse fail. The fuse is alright. If I take it back and go back to there, 0.07 ohms, so it's still working all okay, but it doesn't like to measure the circuit resistance on any of these simulators that I've got. Okay, so I've dug out my little 3-phase motor here. We've set up our MTR 105. We are zeroed. Again, we're on 2Y resistance. So we'll just measure the resistance on this motor winding, and we are 25.6 ohms. We'll have to remember that because there's no hold function on this. We'll take out the leads, and we'll put this into our UT505B. Not zeroed at the moment, but we'll just ignore that because it's quite a high one. And we've gone to 20 milliamp running, and we're over 100 ohms, which doesn't make sense, does it? Let's go and short the leads out. We get 0.07, which is okay. We'll zero it. So we're zeroed. We'll go back onto our motor, and we are 100 ohms again. It doesn't like it at all. I have had instruments in the past that don't like my simulators, but as soon as you put them on a normal motor, they read fine. But this one isn't having it at all, is it? I need to do some more investigation and scope the output to see what's going on with it, really. Let's just knock him off. We'll just put him over onto the standard kilo ohms function, and we've got 26 ohms, which is working fine there, isn't it? So we'll move on to our insulation test function. For the specification on this, all the ranges have a plus or minus 3% plus 3 digits nominal tolerance value to them. In addition to that, there is an extra tolerance to add to this depending upon which test voltage you are using. So for our 50 volt test mode, we can measure from 10 kilo ohms to 10 giga ohms. The additional tolerance is 4% per giga ohm. At 100 volts, we've got 10 kilo ohms to 20 giga ohms, and our additional tolerance is 2% per giga ohm. 250 volts, we are 10 kilo ohms to 50 giga ohms, and we are 0.8% per giga ohm additional. 500 volts, we are 10 kilo ohms to 100 giga ohms with an additional 0.4% per giga ohm, and then on our 1000 volt test voltage we have 10 kilo ohms to 200 giga ohms with an additional 0.2% per giga ohm. We also have a variable voltage function on this as well. So for each of the ranges you can select between 50% to 120% of the nominal test voltage you are using. So there's your specifications. You have a timer function on this that you can turn on and off with the switch there. You can have a lock function as well, which you hold in the timer, and we've got rid of our lock function there. And then press again and we get rid of the timer. We also have pi and dar. To select these, we go through them. So first one is pi, which is 10 minutes, 1 minute, the dar, 1 minute 15 seconds, and another dar of 1 minute and 30 seconds there. So press it again and we'll get rid of that. You also have a comparison function that you can turn it on and off as well, but that doesn't work when you're in pi and dar mode, because they're just after the ratio really. To set all of these up, you have to go to a setup, which is that one there, and hold it in. And then we move to a setup. Here we can do the voltage and what we want to do. If we hit the enter, then move on to the minutes, and we can select the timer function there, whatever you want, all the way up to 10 minutes. And then background is the best way to show that. Enter again, and now we can set the comparison function, and again I'll select depending on which one we want. Enter again, takes you back to the voltage setting. Once you've finished all your settings, you then press in and hold it, and it takes you back to the insulation test function. So to demo the actual insulation test, I'm going to do a polarization index on one of the simulators here. I'm using this one because of the extended measurement range of the Uni-T UT505B that I can test with this rather than my little three-phase winding simulator. I also have a theoretical model for this that I can compare the values to as well. So to kick it all off, we just move to the PI function there, and then we'll hit the test button, and it starts away on itself. You can see we have a timer up here counting up in seconds, and we have the insulation value being measured at that moment in time. So we can let this run and convene at the end of the test to see what the curve looks like. Okay, so 30 seconds to go on the test. You can see here we're still counting upon the insulation value. Our timer's working its way up to 600. I didn't mention you do have the red light on here, as well as a flashing symbol to show you that the voltage is being applied to the test subject. 10 seconds to go now. You will have to keep your eye on the insulation value because it loses that very quickly, and switch straight over to the PI ratio. So 13.9 gigohms at the end there. I've got a PI ratio of 6.26. So the downside to this at this moment in time is that I can't actually recover the insulation measurement values. I can go to the select there, they don't work. Timer doesn't work either. Com button doesn't work. I can save the result on here, and it just flashes up that it's saved it, and you'll be able to recall it. If I hit the pi dar button, all it'll do is lose this value altogether and just switch to the next test function. So you just get the ratio with this instrument and not the insulation test values unless you're particularly paying attention to the actual test. So what I can do is put this up against the theoretical model, and you can see how well it's performed against that, and it's all very respectable values really. There's no real issues there. You will have a little bit of tolerance against the theory side of it, but they are all well within the instrument specifications. So that's the insulation test function there. When I had the motor out to test it on the continuity function, I did also run an insulation test on it and compared it to the MTR105. So I'll put that snippet of video up here so you can view that, and you can see how it got on with that test as well. Once we have got the motor out, we'll just move on to an insulation test on it. I guess would be a good thing to do. Let's go to 500 volts. We'll put our earth on there, we're on there. We can go for a timer. Should be 1 minute, I believe, and let's hit the test button. And we'll see what kind of a reading we get. So we'll log it at 30 seconds there. We are 0.58 gigaohms at 30 seconds. Let's just swap over to our MTR105, just for a comparison. Now obviously we have just measured that, so it doesn't always work out. We've got timing, and we'll press our go button. 178 mega ohms, and counting on this one as well. So come to 30 seconds there. 263 mega ohms compared to 580 mega ohms. So they're not overly in agreement there really, are they? Which is strange, because when we test resistance values it's perfectly fine. So with the lights off, what I will just do is demo the backlight on this. So you see the hold button here that brings it on as hold, freezes the display. If you hold that in, then you'll get another beep, and there's your backlight there that comes on. Fairly reasonable backlight. There's a little bit of bleeding over this right hand side here, but it's pretty good, and it should do the job when you're out in the field testing. So there you have it, there's the video on the UT505B Insulation Multimeter from Uni-T. Bit of a mixed bag, this one really. Voltage AC and DC is fine. Obviously the continuity function on the test resistors was fine, but taking it to a motor and using it on the simulators needs a bit more work. I'm not sure what the issue is with that yet. I'll need to put an oscilloscope onto the output and see if that tells me anything. Resistance function is fine. The capacitance function, our 90 microfarad capacitor, that was within tolerance. We got 93 microfarads on that, and we were within plus or minus 5 microfarads was the tolerance for that one. For the 300 microfarads, that was a plus or minus 15 microfarad tolerance from calculation, and we measured 319.6, so that's a little bit out of spec. And then we come to the insulation test function. I can put this plot up here. This is the average accuracy of all the instruments that I've tested, and you can see it's in the bottom sort of third, the UT505B, but it's by no means the worst of the instruments out there. So overall on the test resistor bank, it seems to have pretty good tolerance. This next plot shows you the actual deviation for all the test ranges on the UT505B itself, and you can see the 250 volt test range showed the most deviation, but when I put that on the motor it was obviously quite a bit out against the MTR105, so we need to do a little bit more work in that aspect as well and see what the issue is there. So yeah, I started out with high hopes, but they've been dashed a little bit unfortunately. But that'll be it for this video. Thanks very much for watching. Hope everybody has a good Christmas and enjoys the holidays, and I'll see you again in the next video.